Okay, so again, there was a problem with the initial stream, so I'm recording half of lecture 8.1, the first half, which was in the morning. And so, in the previous lecture, I defined multiple algebraic structures starting from a module V. So I explained how to do direct sums, tensor products, dual spaces, and last time I spoke about the alternating algebras, and the smallest one and the most important one is the exterior algebra of a vector space, which will be used for mainly for differential forms, which are a kind of exterior algebra built on the space of dual vector fields. Okay, so exterior algebra. Yeah, so last time I proved a very important property. I'm just going to remind that if we have some alternating algebra A, which is some things like that, infinity, let's say A, okay, I, and then if we have V is in A, P, and W is in A, Q, so we have pure elements in this of these degrees, of degree P and Q, that W, which V is, sorry, I don't have finished yet. W, or I wrote it, maybe V W is minus 1 to the power of P times Q, W V. And this is a property that is called graded anti-commutative. So this is called, so graded commutative. Graded commutative. And in fact, we'll have this property even for non-associative algebras like the cochain algebra with the copy product, which we'll study in the part for mesh calculus. Okay, and so now let's define the exterior algebra. Let R be a commutative utility. V be an R module. And the exterior algebra of V, which are denoted by lambda bullet V. I use this symbol bullets. Some authors use it, some do not. I will use it because a similar symbol will be, I use a similar symbol for other graded algebras that will occur in the future. By lambda V is the smallest or sometimes theoretically it can be defined as universal primitive and is the free the freest is some other term, or the free one, the free, maybe not the freest, the free one. The free alternating. So let's recall alternating is it is associative, unital, so it is unique, and has alternating properties. This algebra containing, so this is the smallest alternating algebra. This was graded algebras containing the original space V. Okay. So lambda bullet V is the graded algebra lambda bullet V is the sum E from 0 to infinity lambda P of V, where lambda PV is the space of so-called element of the elements which are called P vectors of degree P. And these are things, so these are linear combination of monomials of degree P. Monomials of degree P is just abstract multiplication of P vectors. So the multiplication operator is denoted by the wedge symbol. So multiplication on lambda V is denoted by alpha wedge vector, where alpha and beta are in lambda bullet V. When they are homogeneous, so when alpha is in lambda P V for some P and beta is in lambda Q V, so here P and Q are integer and natural numbers, then the graded property says that alpha wedge P is in lambda 10 plus Q of V. Okay. So let's give the lowest degrees. So lambda 0 V is R. Is the original ring R. It's spanned by the identity unit element. Lambda 1 of V is one vectors which are just vectors. And lambda 2V is the space or the linear combination of monomials of degree 2. So this is the space of sum E from lambda to sum K lambda 1 VI wedge Wi, where lambda I is a scalar and Vi and Wi are vectors. And so on, lambda 3 will be such sum out of um, three vectors, the Wedge products of three vectors, and so on. Okay, now from the grade, a very important property is that this algebra is in fact, when the original space is finite dimensional, it is also finite dimensional. We'll see how exactly, but especially that the higher order terms will be zero, and the reason is that if there are two terms in such kind of product, V1 wedge to Vk, two of them are equal, the whole result is zero, so let's show that. So position. So let R be a point different utility. V be an R module. Take some vector V in V and some arbitrary for K vector in alpha. It can be mixed, it doesn't matter. Then V wedge alpha wedge V equals to 0. And if you have some elements on the left, some elements on the right, the important thing is that this thing in the middle is 0. So if you have two elements that are the same, the whole result is 0. And the proof is very easy. So because alpha is a sum of monomials, we can need to prove for monomials, and then by distributive property to be true for all alphas. So it is enough to prove for alpha equals V1 wedge to Vk for some integer k, and V1 to Vk in V. Okay, and now let's do the computation, which follows directly from graded-commutative. So we have that V wedge alpha wedge V is V wedge V1 to Vk wedge V, which is because this is a k vector and this is 1, we can swap it with -1 to the power of k, V wedge V1 to Vk, and this is 0, so the whole result is 0. 0 wedge V1 to Vk, which is 0. Okay. And so now, as I said, if we are in finite dimension, then this will mean that high order high degree multivectors are the elements of the algebra are also called multivectors of the exterior algebra. So for a while, let R be commutative ring with unity and V be not so fixed some integer and V be an n-dimensional armor, so it's in fifth dimension. Then we have the following. Let me see if I was able to print. Then we have two things. First, if p is bigger than n, then lambda, the p power of lambda is 0. And second, if p is from 0 to n, so here we have if 0, p is between 0 and n, and then the following p vectors, the p vectors I1, wedge, EY2 to EYP. They are ordered. If they are not ordered, we can order them by interchanging, doing transposition. So it's enough to take only order, such kind of ordered things. E from I1, and then we have strict inequalities for some basis. E1, En of V. So we have some basis of V, and we have such kind of P vectors. Then these P vectors, these type of things here, span lambda P of V. Okay. So maybe I have to do some brackets. Okay, so now let's do the proof. So I'll take this arbitrarily V1 to VP. So V1, VP, V elements of V. Then V1, since V1 went to VP are linear combinations of the basis of V1 to Vn, then V1 wedge with VP. So we have linear combinations of V1 to Vn. We will see this explicitly, but any V1 is some lambda 1 type C1 plus to lambda N1 En, and then we have P of these linear combinations, and when we expand the wedge product, we'll have a lot of terms, but what it matters is that all of these terms will be some coefficient times P elements of the basis. Then so V1 to VP is a linear combination of terms of the type EI1 wedge to EIP, where, so deciding the basis, so 1 is from I1 to, so no, initially we don't have any kind of order, so all of these are and if, in fact, if you work with the tensor algebra, we cannot change the order. So initially the order is, let's assume, there is no order here, just direct expansion from distributive force. However, so if, let's prove one, if P is bigger than N, then there, in any such combination, at least two of them are equal. At least two I1 to IP are equal. So we have a set with at least n plus 1 elements, but the elements are from 1 to n, so at least two of them will be equal. So at least two of them are equal. And by the first proposition I proved, this means that the whole result is 0. And so the whole result is 0. And so we say that if we have at least n plus 1 the degree at least n plus 1, the whole result is 0. And so the whole space is 0. This is 1. Now let's see 2. Okay. Again, we'll continue from this representation. So I'll state it in words. So consider this thing here, this combination A1 to wedge product to EAIP. Because we can reorder them so that the combination is non-decreasing. But if there are two of them, then this is be equal, so we can assume that all of them are different. Now, they are different, and we can order them with some possible sign change. It depends on the number of transpositions, but it doesn't matter for the span of the form. It matters only for some specific calculations. So EI1 to EYP can be ordered with potential change sign. Sign change to, let's say, a J1 wedge a J P, such that 1 is less than A1, J1, which is more than J2. I said in theory it can be some of them are equal if they are equal indices here, but the whole result is 0, so I have assumed that we are in the non-zero case, and JP, which is at most n. And so we see that all such elements are linear sums of this kind of things, but any kind of element of this type is a linear combination of elements of this type. And we show that all elements of this type, EA1 to EIP for unordered I1 to IP, are either 0 or of the type AJ1 wedge to AJP, where all of them are ordered. And this proves our claim, because This is what I want to prove, that the whole space is spanned by such elements. Okay. And so let's give some example in 2D. And yeah, the 3D part is in the recording 10.1b, which was fine. So I will do only degree 2 here. Example. Let v equals. So, it doesn't matter. Consider commutative and v is r squared with base. With the standard basis. It doesn't matter the basis. With basis. Okay, let's take the standard basis. So now take three vectors. So let's take v equals lambda 1 e1 plus lambda 2 e2. This is u. V is mu1 e1 plus mu2 e2, and w is lambda 2. Sorry. Kappa 1 e1 plus kappa 2 e2. Then, so first let's compute u wedge v. U wedge v is, let's rewrite, lambda 1 e1 plus lambda 2 e2 wedge v1, so u1 u1 plus u2 e2. And this thing here equals to lambda 1 e1 wedge e1. So this is what I said, I just expanded everything, plus lambda 1 u2 e1 wedge e2, and do the same with lambda 2. Lambda 2, here I forgot to put u1. Lambda 2 u1 e2 wedge e1 plus lambda 2 u2 e2 wedge e2. Now these things here are 0 because e1 is 0 and e2 is 0, and these things here are the same thing with opposite signs. So the whole thing is equal to lambda 1 mu 2 minus lambda 2 mu 1 e1 wedge e2. So this thing is the same as this, and this is with minus because we interchanged. Now, to finish this example, let's see what happens if we multiply the result code. So this is in fact the determinant lambda 1, lambda 2, mu1, mu2, e1 wedge e2, and call this C. The fact that it's determinant is not by chance. In fact, determinants in exterior algebras are very interlinked, as we'll see. But let's call it this one now C e1 wedge e2. And now this is element of degree 2. And we expect that element of degree 3 will be 0 because the initial algebra is a dimension. Not the initial module is dimension 2. So let's check this. So u wedge v wedge w, we already computed u wedge v. So this is c e1 wedge e2. This is the first part, and w is kappa 1 e1 plus kappa 2 e2, and this is c kappa 1 e1 wedge e2 wedge e1 plus c kappa 2 e1 wedge e2 wedge e2. And here we have this with this, And here we have this with this. So we have to, in both summand we have to equal vector, so we have 0 to 0, and the whole result is 0. And this is because lambda 3v is the zero space. And so lambda pv is also 0 for p bigger than 2 as well. Okay, and with this, I will finish the stream because the next part was successfully recorded before.